Okay, good morning. Should we start at 10 or I should wait for 10 minutes? Do you remember?
I think we start now.
No, okay, so that's good. So we continue the lesson that we started last time about integrals. Let me just try to refresh you a little bit.
Guys,
So okay, so I want to again more or less review a little bit about what we had before and make it a little bit more complete, then we can go faster next time. So the motivating problem for the integrals was trying to find the area which is restricted by three straight lines but an arbitrary curve. Yes, so you want to find the area bounded by three straight lines and an arbitrary curve. So I hope that I could somehow make it plausible for you. The method of rectangles is a good way to do it, and then I solved a problem using that idea of summing up, adding up the areas of the rectangles. Do you remember the process of limiting and things like that, and you were able to get it? So let me now state it formally here. So here what we want to do, I have a continuous function, a function that is, I can draw it with one pen stroke if I want to draw the graph, and I want to look at that function on the interval between a and b. So do you remember I started chopping this interval to smaller pieces and making rectangles and then adding them up. Okay, so if I want to formalize it, I would say that let me start partitioning this interval to n equal pieces. Okay, so n equal pieces, I divide this interval. So the length, the total length of the interval is how much? Is b minus a. Agree? Because from here to here is b, from here to here is a, so the length of the interval itself will be b minus a, and I divide it to n equal pieces, and I call this delta x. Yes? So the delta x is the increment in x when I go one step to the right. So this is the notation that I am introducing. This is called my delta x. So for example, if I want to concentrate here, the first point, when I put my first point here, let me call it x1. If I ask you what is the distance from A to the first partitioning point, I mean this length is this number. Yes? And then I go to the next number, the next point, x2. So this is delta x. This length is also delta x. The length of the next one is delta x. And then I continue until I reach to there. Yes? So I continue, for example, let me just write it like this. Let me put some dots here. So assuming that I continue this process. And at some point I reach to x sub k, for example. Let me write it x sub k minus 1. And then the next one will be x sub k. And then, of course, I will continue this method. So what I want you to do is just concentrate right here. But do you understand what I am doing? So from A to B, I am chopping it up into n sub-intervals. The first point, I call it x1. The second point, I call it x2. And I will continue. I reach to some level x sub k minus 1. The next one becomes x sub k. Of course, the next one becomes x sub k plus 1. And I will continue until I reach to B. Yes, is the setup clear? So each one of these sub-intervals has the same length delta x. So here, this is 1 delta x, this is 2 delta, this is another delta x, continue. But in this terminology, it is good to see that, let me call this one x node, x0. Of course, I give you A and B from the beginning, but if I want to make the notation very smoothly, it is good to give it another name x node, and let me call this one the final point, which is xn. Yes? Okay, so if I ask you what is delta x is that one. You can also write delta x is any x that you like minus its previous one. Do you agree? That is also another way to say delta x. x1 minus x node is delta x. x2 minus x1 is again delta x. Or in general, any number from minus the previous exact number is delta x. That's also one way to do that. Do you remember what was my goal? My goal is to construct a rectangle here, for example. I don't want to draw all the rectangles because it will mess up the figure. But assume that you have this, and I want to make this rectangle here. Yes? If I ask you what is the area of this particular rectangle, by the way, this is interval number 1. The second one is interval number 2. So when I say interval number 1, the right-hand side index is 1. Interval number 2, it starts with x1, ends with x2. So when I say interval number 1, I need to look at the index of the right-hand side. Yes? When I say which interval is this is not the first interval. This is the second interval. Do you agree? So if I ask you what is the kth interval, the kth interval is from xk minus 1 to xk. This is the kth interval. Yes? Is that understandable? Okay. Now can you tell me what is the area of this rectangle? So this rectangle is the kth rectangle. Let me call the area of the kth rectangle to be a sub k. If I ask you what is a sub k, you can immediately answer that to me, yes? What is the value of a sub k? It is the width of the rectangle, which is delta x, multiplied by the height of my rectangle. So what is the height of my rectangle? What is the height of my rectangle? If I want to write an expression, of course you cannot give me a number here, but you can write an expression for the height of the rectangle based on these numbers and the function. So what is that? Yes?
F of x, k minus 1.
K minus 1. So this becomes f of x sub k minus 1. Yes? If I multiply these two, this will give me the area of the kth rectangle. If I start calculating the area of each one of these rectangles and add them up, it becomes approximately the area below the curve. Yes? So if I consider A to be the area below the curve, this is my target, it is approximately equal to sigma of all these areas. K goes from 1 to n. I am adding the areas of each one of these sub-rectangles from the first rectangle to the last one, which is the nth rectangle. Yes? This is approximately equal to the area that I want. But instead of a sub k, I can replace it with that one. So this becomes equal to sigma. K goes from 1 to n. Let me write f first. F of sub k minus 1. multiplied by delta x. Yes? And then this is approximation. Do you remember what was the trick to go to intuitively towards the exact value? What was the idea? Instead of chopping it to n parts, let me chop it into infinitely many parts. Apparently it was not practically possible, because it is not possible to divide something infinitely many times. But then I hope that you remember, with some tricks we were able to really use that and find the error. So I want you to the only thing that I want to do is to make this formula plausible for you. So it means that if I calculate this sum, but do it infinitely many times, technically it means take the limit of this sum when n approaches infinity. I hope that you agree this is plausible to write equal inside now. Yes, that is the only thing I wanted you to understand. So this limit will give me the area of that. Okay. Here, the one thing that I want to make it clear, it becomes a little bit more advanced mathematics. For a continuous function, it doesn't matter which value in the subinterval you concentrate on. Here, I constructed based on the minimum value. Yes? But I could do the same thing for the maximum value. Yes? For example, instead of choosing this, I could choose the highest one. Then I have to make this rectangle. In the previous case, each rectangle that I consider is smaller than the area that I want by this amount. So I am making that much error. But I always underestimate this, the area. But I can also use this one. Then I am actually having a little bit extra area. That is my error, but I am overestimating. But the point is that if you consider the minimum rectangles, when you increase the number of subintervals, the values increase and getting closer and closer to the real area. But if you consider these, the areas become smaller and approach the real area. Okay? You need to take this for granted. And then something very interesting happens. You really don't need to care about minimum and maximum. You can just choose any random number in that interval and put it there. It will work. Okay, so this is why the area, this is probably not very intuitive, but you need to trust me on that. So if you have a well-behaved function here, continuous, I can write f, but instead of choosing the left point or the right point for minimum or maximum, I can choose any point that I like. So let me write it with letter, for example, alpha I delta x. Alpha I is any number in the kth, this is not alpha I, this is alpha k. Any number in the kth interval. So, I motivated you only for minimum values, making this smaller rectangles, but you can make them the larger rectangle, or you can choose any number in between and make another rectangle on top of that. This will work, okay? So this will give you the area. So what I want you to understand is that this limit pops up actually in this context. Okay? Now let us change the problem in a different problem. Let us consider physics problem now. Okay, now I ask you one question. You have a moving particle in a straight line and one dimensions only, and then I give you the speed of the particle is constant 2 meters per second, yes, and I ask you how much this particle displaces if you wait 5 seconds, for example. So what will be the answer? The speed of the particle is 2 meters per second constantly, and then you wait only 5 seconds. How much this particle moves? 10 meters. Yes? So that is very simple. But now, If I give you a particle which is accelerating or decelerating all the time, and I want to ask you the same question. So I have a particle, still the particle moves in one dimension, the problem is as simple as that, but the speed is not constant. The speed is changing over time. Yes, so the speed of my particle is not a constant number, but the speed of my particle is a function of time. I give you this function, and I give you the total amount of time, and now I ask you the same question. I want you to tell me, after this period of time, how much the particle has moved. Okay? For the time being, let us make the problem simple. The particle will not return back, so it is always moving in one direction. I want you to think about this problem. This problem is not as easy as before, as simple as before. So do you have any idea how to solve this problem? Is the question clear? So I have a particle, assume that this is the origin, and the particle starts from the origin and always goes to the right, but with different velocities. Yes? The velocity will go up and down, but the constraint is that the particle will never return to the left. It's always constantly going to the right with different speeds. And then you wait for, I don't know, t seconds. And then after t seconds, you want to answer this question: how much is the distance from the particle to the origin? Assuming that I give you how the velocity is changing over time. For example, I can tell you that this particle moves in a way that its velocity at time t is 2 times t. For example, I give you the functional dependence, but then I want you to ask a question. So how should we solve the problem? Or how do you tackle for finding a way to solve the problem? So can I say that, okay, I multiply, so I calculate Vt or V, then it becomes 2t, and then I actually, what do? I just multiply 2t and by velocity. So this is clearly not possible, yes? So do you have any idea what to do? The idea is very, very similar to that trick, but in a different context. So you say that, okay, if this is the t-axis, let me take it time axis. Okay? This is the origin of the time, and the particle starts now, and then you want to wait t seconds. So let me instead of t seconds, let me clean this. Instead of t seconds, let me say I wait 5 seconds. And I give you the functional dependence of the speed on time. I want to know how much the particle moves when 5 seconds is passed. So what I do, I would say that, okay, let me start subdividing these 5 seconds into smaller pieces. Yes? Okay, I will divide it, for example, into 1, 2, and 3. So I have 4 pieces. And if you don't mind, let me make it 8 seconds so it is easier to chop it up without working with decimals. So this becomes second number 2. So 2 seconds, 4 seconds, 6 seconds, and 8 seconds. Okay, so if I ask you how much the particle is moved only during 2 seconds, what can I do? I would say that let me take the speed at time 0 and multiply it by 2 seconds. And I tell you that this is the displacement of my particle during 2 seconds. Do you think that this is precise, this sentence? Why not, Ruben?
Because it's such a long time.
Yeah, it is probably, it might happen that this particle is really moving up and down very fast, so even 2 seconds is very big for it, yes? So but at the end, what I am saying is that if I calculate this, it will give me not the exact displacement, but an approximate displacement. Is that understandable? So this is the displacement that I do on the first interval approximately. Now, the particle has moved this, and then now the particle is here. Now I will take v at time 2. I can calculate this because I told you that I give you this formula. So you put 0 in that formula, you get this multiplied by 2. It gives you not the exact distance that is traveled, but approximate distance. And now you go to the next interval. I calculate the speed of my particle at this instant of time, and then I multiply it again by 2 seconds. This gives me approximate displacement of my particle on the second interval. Not exact one, yes? And I do the same thing here. V at 6 multiplied by 2, and finally I have 4 times 2 and 1 more. 6 times 2. And then if I add them, I cannot claim this is the exact displacement, but it's an approximation for the calculation that I want to do for the displacement. Yes? Is that clear? So this is approximately equals to the distance traveled. But let me, instead of chopping it to this one, let me subdivide each one, and then let me consider this. Yes? Now let me, instead of waiting 2 seconds and calculate this in 2 seconds, let me wait this time 1 second and do the same calculation. So this time I calculate v at 0, but instead of multiplying by 2, I just multiply it by 1. And then when I go to the second interval, I calculate a speed at 1 and multiply it by the interval 1. And I do the same thing here, yes? V2 multiplied by 1, and then I will continue V7 multiplied by 1. This is also approximately the distance. Yes? But I hope that you agree with me that this approximation now is better than the previous one. Do you agree? Yes or no? Okay. So you see, more or less, there is no area involved here. But the process that I am doing it is very similar to the process when I was doing, when I was calculating the area. Yes? Okay, so now, if I want to solve this problem, what do? I can write that I will V, if I divide it into n equal pieces, then I can say that delta t is the final time minus the initial time divided by n. Okay, instead of doing it into, I don't know, 4 intervals or 8 intervals, I divide it into n intervals. And then what I do, I calculate v at the left-hand side, for example, x sub k minus 1, sorry, t sub k minus 1, and then multiply it by delta t. This will give me the approximate distance traveled by my moving particle on the kth interval of time. And then if I start adding them from the first moment to the last, this still gives me an approximation for the distance traveled by my particle. Yes? But then, if I want to make the exact distance, I will do the same thing. I will subdivide my interval to infinitely many times by taking the limit of this combination, n goes to infinity, and then hopefully I made it plausible for you that this should be the exact distance. Yes? Is that right? Because if I make this interval very, very small, the particle doesn't have enough time to change its speed, yes? So I could say that the speed of my particle is constant over that very, very small short time. And then I can use this one. But now compare the structure, of this limit that you see here, which appeared in physics, with the structure of that limit that appeared in geometry for area. Everything is the same. Do you feel the structures are the same? Only the letters are different. So this means that this limit appears once when I wanted to calculate the area, appeared another time in a completely different context when I wanted to calculate the total distance traveled by my particle. So again, hopefully, and there are numerous examples of these kinds, that this limit is very important. Okay, it appeared here in physics, it appeared here in geometry. I can give you a lot of examples that it will appear in a lot of places. So again, when something appears a lot in mathematics, mathematicians give it a name and try to study it. Yes? And this is what we call integral. Yes? Is that understandable? So this kind of limit is important. By the way, these are called Riemann sums. So the Riemann is was actually a very genius mathematician from Germany. I'm not sure about this should be double M or not, but actually, and unfortunately he died before 40. Okay, so these sums that you see are usually called Riemann sums, and this integral that we study is called the Riemann integral. But now that I hope that you agree with me that this limit is somehow important, now let me officially define you the integral. So definition. Okay, first let me ask you, do you have any questions regarding these things? So far I wanted to try to show you that this limit is important. So it deserves a name and deserves investigation. So definition. So let me now start this. Let f be a function that is continuous on the interval a less than or equal to x less than or equal to b. The limit limit of sigma f of alpha k delta x, k goes from 1 to n goes to infinity, where if I ask you what is delta x, you say delta x is b minus a divided by n, and alpha k is somewhere between and alpha k, let me write it in this way. Oh, there it is. So, and alpha k is in the kth subinterval is an arbitrary number in the kth interval, kth subinterval. Is called the integral. By the way, the adjective usually used is definite integral. Integral of f on the interval and it is denoted by integral from a to b f of x dx. So in other words, if I want to write a formula for you, you can say that integral from a to b f of x d of x is equal to the limit of this Riemann sum. But of course, this is much more complicated than the limit that we face for derivative. And I hope that you agree. Even in the earlier days that we were talking about the definition of the derivative, we were able to solve a lot of functions using the definition. But even for very simple functions, do you remember? I did it for you before. Calculating this limit is actually not very simple to do, and I told you that, if you remember, sometimes impossible to do. Okay? So it is not like derivative. So by the way, this integral sign is a good choice. This is a stretched S because of sum. Yes? So whenever this you should be back in your head. Whenever you are calculating an integral, you're calculating a sum. Okay? Summing, but when you have sigma, you have finitely many terms. But you have integral, it means that you are adding up infinitely many terms. So at the end, integral is a sum. So, and this is why they have chosen this stretched S to denote that this is a sum. Yes? I have even seen older books really write it as an S, A to B. But usually this is the symbol that we use. Okay. And then dx is more or less the same thing as delta x, because this you need to understand a little bit more advanced mathematics. But dx is the same delta x, but delta x happens when I have finitely many subintervals. Dx is the same delta x, but much, much, much shorter when I have infinitely many subintervals. You can imagine it in that way. Okay, let me ask you one question. Do you think that an integral can be negative? You see, the integral is the limit of such a sum. Can an integral be negative? I want to test your understanding. Can an integral be negative? Yes or no? Okay, you can think about so that I'm cleaning the board. Can an integral be negative? The people at home, if they want to answer, you have to talk to me because I cannot see the chat window. Okay. Can an integral be negative or not? What is your answer? Can it be yes or no? So you say no. What?
So it might be able to, because the function can go below.
Yeah, exactly.
And
exactly. It can be cases that the integral is negative. Why is that? For example, I can have this function. Of course, in that context, in the case for area, it doesn't make sense, but be careful about this. Here, if I have my function below the x-axis, then when I start making these intervals, okay, what happens? Be careful. The notion of integral has some relation to speed, to distance, to the area, but it is completely an independent identity in mathematics. I just use these simple examples to motivate you why this is useful. But now this is an abstract object in mathematics, independent of any other ideas. Yes? So I'm asking you about, is it possible to have an integral negative? The answer is yes. Assume that I have this function, which is lying below the x-axis, and then I have to calculate this. Delta x is always positive. Agree or not? Delta x is the last number minus the first number, which is always positive, divided by n. So delta x is always positive. But f of this number sometimes can be negative, yes? If I choose this, if alpha k is this one, f of alpha k is a negative number. And assume that this is my function, so all the f of alpha k's are negative. All of them are negative, this number is positive, so I have a bunch of negative numbers that I am adding. And then definitely I will get a negative number. So be careful, the integral can be negative. You can also imagine, can the integral be 0? For which function? A very trivial function. The constant function from here, because all the heights are 0. So then it means that all these numbers are 0, even though they are positive, but the product is 0, and when I add them up, it becomes 0. And when I take the limit, it is still 0. So be careful. Integral is not a function. Integral is a number. That number might be positive, 0, or negative. Yes? So be careful about your interpretation. Okay, now for example, let us explore some properties. For any function, if I write this, what do you think will happen for my integral? I'm sorry. From A, but I go to A. Can you, what do you expect for the number in this case?
0.
Why?
Because the interval is like...
Exactly. Don't say because the area is 0. Because I'm asking you abstract, think abstractly. Integral has nothing to do with areas. Yes? Integral is this limit. For some problems, interpretation of integral is area. For some problems, interpretation of integral is the distance. Okay? So integral is an independent entity. But why this becomes 0? Because I have to calculate this Riemann sum. What is delta x? Delta x is the right-hand limit minus the left-hand limit divided by n. But if the lower limit and the upper limits are the same, so what I calculate, a minus a divided by n, which is 0 divided by n, which is 0. Of course, I don't know about these numbers, but I don't care because delta x is 0. When I multiply here, it is 0. And I have a bunch of zeros that I am adding and making the limit. So what will happen? What will happen? It becomes 0. So remember, if you have a definite integral, from a number to itself, the answer is always 0. You really don't need to calculate anything. Is that understandable? Okay. This is one thing that I want you to understand. But now I want to try to motivate you a little bit about it. Still, the problem is still standing. We realize calculating this limit is hard and sometimes impossible. So now, do you think that this integral is a useful concept or not? Because if this is sometimes not practical to calculate and sometimes impossible, even though this seems a nice concept, it is useless because we cannot calculate it. And I want you to understand this is a serious problem. Even though this is a nice theory, but from practical point of view, it is not valuable that much if we cannot calculate this. And of course, it is clear that it is hard. We cannot find any way unless you are so smart to see the problem from a different perspective. If you just want to force yourself to calculate these limits, there is no way. This becomes really hard. And that was the genius of Newton, to discover that for one particular case, calculating this limit is very simple. And then let us try to motivate you by that diagram. Okay? So, now let me try to clean these. We don't need them. Okay, so Newton actually realized that let us calculate the Riemann sum not for the function, for its derivative. So it's apparently Newton making the problem harder, because you had troubles with calculating the limit for the function itself, but Newton now asking, let us calculate this not for f, but for f prime. Okay, so it means that Newton is now interested in to calculate this. This is the question he asked. Let us calculate this one. Okay, if I want to calculate this one, tell me what should I do? Integral from a to b f prime of x dx is equal to the limit sigma k goes from 1 to n. Okay, so let me choose the previous version, x sub k minus 1 prime and delta x, n goes to infinity. Yes? So do you agree? If I take this definition and replace f with f prime, I will get this. Yes? You might say, what is the benefit of that? I want to try to motivate you, not 100%. I want to try to motivate you. This limit becomes a little bit simple to calculate, much simpler to calculate. Okay, I want to motivate you about this. Okay? Is that understandable? So what I am doing, I am just changing f to f prime and writing it again. But now where is f prime of xk minus 1? I want you to really help me to do this, because then you will understand a lot of good things here. Okay? So this is my delta x. Can you tell me what is f prime of xk minus 1? Do you remember the interpretation of derivative? What is that? F prime at this point is what? Yes?
You take a chord on the xk minus 1 and then you follow this up
Yes?
until you intersect the
Yes?
graph, and then you take a line tangent.
Exactly. And then the slope of that tangent line is this number. Agree? So I do exactly the same thing as Dylan mentioned. Thank you very much. So I go up here, and then I get this point. I draw the tangent line. The slope of this tangent line is actually the derivative. Yes? Okay, but now, can you tell me, so the slope of this tangent line is this number, but now can you tell me what will be this approximately? Or no, exactly, and then I will do approximation later. Then what will happen if I multiply the slope of that by delta x? Okay, let me make it the picture clear for you. So let me draw a horizontal line here for you, and then complete this very small rectangle, sorry, very small triangle. If I ask you what is this is delta x. Yes? And now let me ask you, let us momentarily consider this angle to be theta. If I ask you what is tangent of theta, you can answer this question. What is tangent of theta? The tangent of theta is this length divided by that length. Do you agree? So this becomes, let me call this length y number k. The y coordinate number k, and then I would write y number k divided by delta x. Yes? If I ask you what is tangent theta is a slope, is the slope of the line. So it is, as Dylan said, it is f prime of k minus 1. That is the meaning of a slope. Yes? And then it means that when I multiply everything by delta k, f prime xk minus 1 times delta x becomes y sub k. Yes? So what is happening, this combination is this little distance you see. Yes? So this becomes limit of sigma y k, k goes from 1 to n, n goes to infinity. Agree or not? So if I ask you what is this, if this is derivative, then the interpretation of this product is this distance. Okay, tell me, if I increase the number of n, how this will affect yk? this yk becomes smaller. Yes, and it becomes close to this distance up to the graph. Yes, so if I increase n, it means that this value for a small n becomes only this part if I have infinitely many partitions. So these length becomes smaller and then becomes comparable to this length. So what happens when I am adding these vertical distances? It means that I do it for this, I don't know, I do it for the previous one, you see. So let me just draw this one as well. So I do the same thing here. I get another y here, another y here, another y here. So when I am adding these y's, I am adding how much my function is changing at the end. Yes? If you have two floors, if you want to find the distance between two floors, one way is to directly measure the distance, and another way is to measure the height of each step and then add them up. Is that understandable or not? So what I want you to understand from geometrical point of view, when I am calculating this, I am adding the heights of each stair when I am going up. This is one way to understand it. But another way is that you calculate the height at the end. Do you agree that if I start adding these distances, I will have the whole height? Yes? Yes or no? Agree? Okay, now can you tell me what is this height now? This height is from here to here minus from here to here. From here to here is f of b. From here to here is f of b. From here to here is from here to here, which is f of a. So I calculate the difference. Yes? Yes or no? So you see, Newton was actually smart to understand that for one particular case, I can calculate this very easily. And that is the case when this function is not the function, it's the derivative of a function. Yes? Because when I replace the derivative of a function in the definition of the integral, as we understood it from this picture, this sum becomes the sum of these vertical distances. Yes? And when I make this n going to infinity, I hope that you agree with me. What you are calculating these heights. You can calculate it in this way, or you can calculate how much I have the difference from the first point to the last point. And that number becomes this. Understandable or not? Now do not look in the middle. You calculated the integral. Integral from a to b f prime x dx is just f of b minus f of a. Yes or no? So this means that, let me move it up. So this means that integral from a to b f prime of x dx is not hard at all. You just calculate f at b minus f of a. So this is Newton's formula actually. I hope that I could motivate you. Of course, there are some details if you want to make it very rigorous, but it was very intuitively clear, hopefully. Yes? Yes or no? If you have any questions, let me know. So what I did, in this calculation, I started calculating all these small vertical distances and add them up. But I hope that you agree, when you add these vertical distances, at the end, what you get is the total distance. Yes? So the total distance can be calculated in two different ways. One way is to calculate it like this. One way is to calculate it like this, which is the integral. So these two numbers should be equal. Yes or no? Okay. Now, this is why primitive function becomes important. So what you are doing when you want to calculate the integral, if you succeed to find a function whose derivative is sitting here, then you are done by very simple formula. So when I give you integral from a to b f of x dx, you need to find a function whose derivative is little f. What is that function? Give me a function whose give me a function whose derivative is f. What is that function called? What is that function? There is a name for that function, yes? Give me a function. What is the name of the function whose derivative becomes little f? Primitive function. And primitive function is denoted by capital letter F. So then it means that fb minus fa. So you see, I want you to understand this is exactly this thing written here. This Newton's tells you that if you have integral of the derivative of a function, you just ignore the derivative and write this combination. Another way to see this means that the function that you write here is the function whose derivative you see here. Now I start from a function without prime sign. What I have to write here is a function whose derivative is this one. And that is famous, that is primitive function. So then it means that this is the Newton's formula. So you see that. This is why primitive functions are important, because if I can find a primitive function, I can calculate integrals very, very simply. Is that right? Okay. Now my recommendation is that if you don't like these kinds of discussions, no worries, you really don't lose anything if you just know how to use the formula. But if, I don't know, if you are curious about to understand how formulas are actually discovered, this is one way to understand. Okay? Is that clear? Okay, now from this lesson, I don't know how much time we have. Yes, we have a little bit of time. From this lesson, I would try to concentrate on calculational points, not conceptual ones. And I would say that you cannot be good in calculating integrals unless you are very good in calculating primitive functions. So when I started calculating, teaching you primitive functions, that was just a mathematical curiosity. But now you realize why this is in principle important, because this integral appears in a lot of applications, so it is important to us. But unfortunately, the crude model of calculating the integral is not practical at all. So we need to find an alternative, or we have to say goodbye to all those nice practical applications. And then Newton realized that, okay, this would be possible if, of course there is a big if I can find a primitive function. But finding primitive functions turns out to be much simpler than calculating these integrals. Yes? Okay? Okay, so now let us try to give you some examples, and then I will write the formula, Newton's formula here. So integral from a to b of any function, any continuous function on that interval is equal to f, capital F, a primitive function for f, calculated at this upper number, minus the same primitive function calculated at the lower number. So this is the very important formula here. By the way, you immediately see this formula turns out, yes? If you have integral from a to a, then it becomes f of a minus f of a, which is always 0. Yes? Okay, and then you realize sometimes integral can be negative, yes? Because who knows? Might be the primitive function is in a way that this number is smaller than that number, then it turns out to be negative. Okay, now let me give you one example at least to start. So this example is important for you, for example, yes? But all the things that I have talked about are important if you really want to understand. So example. Compute the following integrals. Okay, what is my first example? Let us keep it very simple. So integral, I would write from minus 1 to 3. Then I would write x to the power of 2 dx. I want to calculate this. Actually, this is a very, very simple problem even in Math 3C. So if you want to calculate this integral, this is the only way that you can do at your in your level. So what you do, you need to ask yourself, can I find a primitive function for this? I hope that you understand. What is a primitive function for that? Do you remember? X3 divided by 3. So then I would write, be careful by the way, there are some things I have seen people make mistakes. So the process of finding a primitive function is finalized. You are not allowed to keep the integral sign. Be careful. You have to drop it because primitive function is found. And then instead, you draw a vertical line in front and put -1 to 3. Yes? So be careful. If you just put integral again here, that would be wrong. And then what I am supposed to do, I have to replace the x with 3 according to this, replace x with -1, get the result and subtract them. I recommend you, if you can do it in your head quickly, just do it of course, but otherwise I will draw it like this. I put 3 here, so this becomes 3 to the power of 3 divided by 3, and I calculated. 27 divided by 3 is just 9. And then I put -1 here. -1 to the power of 3 divided by 3, this becomes -1 over 3. It's not mandatory, you can do it quicker. But for the first example, I would say that I go back to horizontal now. I write the number above, always and always negative sign, and then I write the number below, which includes another negative sign. Yes? Then it becomes 9 plus 1 over 3. The answer is 28 over 3. So the value of this integral is 28 over 3. Understandable? So what I say is that usually we shouldn't give so many examples for integrals, because what you have to do is to find a primitive function, and then the new lesson is just trivial. Put the numbers in your function and subtract the values. So the main thing that you need to improve your skills at is to learn how to find primitive functions for hard problems. Yes? Okay. Okay, I told you what is the meaning of dx here. That is just delta x, but a very small version of that. But another duty for this dx for you is to designate the variable. It might happen that you have more than one letter in your function. When you see dx, this letter means the x is variable. So if I have a here and x here, it means that consider a as a constant, x is your variable. So this is another role of this dx. And by the way, this function has a name here. This is called the integrand. So I want you to know this name. The function under the integral sign is called the integrand. And this number is called the lower limit, and this number is called the upper limit. If you want the name for this, this is called the differential of x. The differential of x. But as you don't need to bother about the names of that one. So that is the role of dx here for you. Any questions? Okay. So, I don't know. Let me give you another one. So, integral, for example, from 0 to ln of 5. And then I give you e to the power of 2x minus 3 e to the power of 4x dx. So we want to calculate this integral, okay? And by the way, when I ask you to calculate the integrals, even if I don't mention it, I always mean the exact value, unless I mention to give me approximate values. So be careful about this one. So if I want to calculate this integral, what I'm supposed to do, first of all, I have to find a primitive function. A primitive function for my integrand. I hope that you haven't forgotten that. So what is the integrand? What is the primitive function? And by the way, do you remember when we found primitive functions, we had some constant c? Do I need to bother about the constant c when it comes to integrals? Why not? Yes? Yes. Because whatever you choose for C, it will appear here and there, and they are gone. So don't bother about that constant C part when you are dealing with with integrals. Yes? Okay, good. How should I calculate that? Can you help me? What is an integrand? Sorry, what is a primitive function for this integrand? Yes? Yes, so it becomes, by the way, so I have to respect the way to have to write it. So I would write 1 over 2 e to the power of 2x. Okay, then minus 3 divided by 4, 4x. Now, am I allowed to keep the integral sign? No, because the primitive function process is done. So I have to put a vertical line in front if I want to, and write it from 0 to ln of 5. Yes? And now I have to divide it into two parts. I replace every appearance of x with the upper limit. So this becomes 1 over 2 e to the power of 2 times ln of 5 minus 3 over 4 e to the power of 4 times ln of 5. Be careful, if I haven't mentioned to approximate values, you're not allowed to put these numbers in your calculator. If you can simplify it, simplify it. Other than that, you have to leave it like that. But here in this case, I hope that you agree with me, I can simplify a lot. How? Do you remember? E to the power of, I don't know, b ln of a. If I want to simplify this, I can write it as e to the power of ln of a and then raise to power b. Do you agree that they are equal? Yes? Because these exponents will be multiplied. But there is a very simple way to do this. E to the power of ln of a. Do you remember what that is? It's a. So this one is a, and then I have a b on top. So remember, e to the power of b ln of a is nothing except a to power b. Yes? So then it means that I have 1 over 2 here, and then I have what? I have a, which is 5 to the power of 2, minus 3/4, and then the same thing here. A, which is 5 to the power of 4. Yes? And then I calculate this one. So this becomes what? 25 over 2. This becomes 625. Yes? And then I have minus divided by 4. So this becomes 50. This is the number that I get. Yeah, please check my calculations if you see something is wrong. Yes, I think it's correct. And now I go to the 0 one. I put 0. But e to power 0 is 1. So this becomes 1/2 minus 3/4. So this becomes minus 1 over 4. Yes? And now I go back to horizontal. I write the number that I got above in its entirety, containing every sign and everything. And then always and always minus the number that I got below, which includes another negative sign. But then I can simplify it a little bit, so it's minus 4 plus 1 over 4. And the answer becomes minus 1,824 divided by 4. Okay, if I divide by 2, it becomes 912, and then divided by 2, so it is minus 1. Yes? So the answer is negative, as you see. And so it is another confirmation. So here we calculate an integral, it comes a positive number, and I calculated this integral, it comes a negative number. Is that okay? Understandable? So you see that, so might be this, the reason that I brought this example, because probably that's the hardest one, that you have to calculate values exactly. Yes? But other than that, this one is needs attention. And then if you go to the university, finding this primitive function takes you a lot of time to learn for different functions. And that is the hard part usually when you want to deal with this integral. Okay, so I think that is a good place to stop, because might be you are still a little tired now. And I will continue. There is one part of the book which is talking a lot of numerical calculations, but these are not actually included. So for the first reading at least, I don't know if you get time to go back to it, I will drop that and I will go to the areas. And then if we get time, I will come back and complete that part as well. But this is not included in the lesson. Any questions? No? Okay, so thank you very much.